Hello, class. Yes, I see that my microphone is on, and it is a beautiful day to be locked in the house here with the curtains pulled, making up lectures. I can always tell the difference between my early morning lectures and my late afternoon, late night lectures, uh, just due to my attitude, if nothing else. And we've got a great series of lectures today on one of the most important things in mechanical engineering in this course that you're going to learn is shear force and bending moment diagrams, and also how they extend then past just the shear force and bending moment diagrams, which I'll explain. But we're not going to get deep into the integrations, the constant integrations that would go on to show the deflection and everything else, except in the most simple of examples. And then, but I will go through that in a simple example of just a simple beam, and then we can figure out going all the way down. This won't be now. We're just learning shear force and bending moment diagrams now. But when we learn the equations that then turn those shear force and bending moment diagrams into the stress, the shear stress, and the normal stress inside that beam, that is going to be the important part. Now, the way that I want to start this is this discussion is I want to look at that last problem that we did, right? Now actually, I think I made that 9 long, didn't I, or whatever. We don't necessarily need that. It's going to be the same. The shear force and bending moment diagrams are going to be the same, whether I make it 9 meters long or 6 meters long or whatever. The scale might be a little different, but the form of the shear force and bending moment diagrams will be the same. So let's just look at this is called the loading diagram, and I think everybody understands why it would be called the loading diagram, right? Because it's where the loads are, right? So we're going to place the loads, and in fact, this is 1, 2, 3, 4, 5, 6, 7, 8. What do you know? I made it one less. But the good part about that is that I now can draw the force P, and I think we made the force P equal to 100 newtons, and then that made the reactive forces R sub A, right? It's only supported by these two supports here. It's a simply supported beam. And you know what I'm going to do is I'm going to drop down some dotted lines so that we see what the extent of the beam is. And what we're going to do underneath it is we're going to make shear force and bending moment diagrams. And we already did this for this one, but I'm going to sort of extend on this. Now, before I get into the shear force and bending moment diagrams, we should talk about the convention of what's positive and what is negative, right? So if I were to have a beam, right, a beam like that, and I was to load this beam with a force P, just like I have, that would cause the beam to bend down like this, right? I think everybody can see that. And we define that as positive, right? So yeah, I could put other forces on there too. But if we have, let me just draw another one. It doesn't have to be as long, really, because if we were to have a beam that came up like this, and you're probably saying, well, how in the world would we get a beam that came up like that? Well, I could support something like this, couldn't I? Now, this isn't a simply supported beam. This would be a complex supported beam. But what if I had it supported there, and then I had it supported here, right? And I placed a force here, P1, and I placed another force here, P2. Then I think that everybody can see that what would happen is we would have a sagging or a positive curvature there, and we would then have a negative curvature there. Does everybody see that? So this would be negative, just like this is negative, and this would be positive. And so on the bending moment diagram, we would assume that in this section, the bending moment would be high, and in this section, the bending moment would be negative. So positive bending moment, negative bending moment, negative bending moment, positive bending moment. So that's what we want to do. And in fact, we've got that all set up here, and we're going to assume, right, we'll assume with this loading, just by looking at it, that it's going to be a positive loading, isn't it? Now, since it's right in the middle, we really have that equation that says that P equals R sub A plus R sub B. All right, so we have this. So let's do analysis on this first. Let's find out, right? So first, we have the loading diagram. And you, or a civil engineer you're working with, or electrical or mechanical engineer you're working with, when you dry it up, look at all the loadings that are placed on the bridge, placed on the floor, joists, you know, things like that. So we come up with a loading diagram. Then we sum the forces in the y direction equal to 0. That's the second thing that we do, and we've done that, right? We summed them equal to 0. That's where we got minus P plus R sub A plus R sub B. But we still have one equation, right? We'll call that equation 1. We still have one equation with two unknowns. And so the third thing that we're going to do is we're going to sum the moments, right? It's not spinning. So we're going to sum the moments at point A. Could it be point B too? Sure. Anything that's going to take R sub B or R sub A unknowns out of the equation. You know what I forgot to do? I forgot to set my timer, and I'm assuming that we've gone for, I don't know, I say about 5 minutes. So let me set the timer. You know, it's early, I don't have everything set up. Let's set that timer. We've had some longer lectures lately, but that's because we're going over, you know, information that's obviously getting a little more difficult, new things that you've never seen before. And I know that you've never seen these before because you're not mechanical engineers, right? And so we have to really, you know, look at this. This is a very important material for your career because, you know, I'm an electrical and a mechanical engineer, right? And they interplay with one another. You know, I haven't, you know, got the companies. I've got 3 companies now that I own, and I've had 8 companies throughout the course of my life. One of those companies wasn't successful, but the other ones were all successful. And you know, those both the electrical and the mechanical have definitely entered into my life, and both of those equally have you know, added to the success I found in my life. And that's what I want to point out for you too. Don't just be an electrical, right? My father was a civil, so I got a lot of, you know, the civil aspect out of that too. So anyway, let's get back to this. Be the consummate engineer, where you can, you know, go and talk about engineering and all different things. The only thing I'm not very good at is chemical engineering. You know, I was never good at chemistry. So, you know, chemical engineering, I'm only trying to learn it right now. So the second thing we're going to do is we're going to sum the moments. Now, it doesn't have to, like I say, be about A, but if we sum them about A, then it's going to take R sub A out of the equation, isn't it? So let's do that. Let's sum the moments about A equal to 0. I'm going to do that up here because I've got some room. So R sub A, well, that's nothing, but we've got P times 100, P equals 100 newtons, and that's 4. I'm just going to put that there. And I'm also going to drop down this line. Why am I dropping this line down? Because that's where P is applied, right? And that's going to tell us a lot. If you remember what we did in the last lecture, where P is applied, if I was to break the beam there and sum the moments on each side following my convention, and let's not forget that convention, right? Wherever we mentally break the beam, and this is easy to remember too. I remember it as ruck, right? Right side, this is my right side, this is my left side, up clockwise, right? And then we have to have exactly the opposite. I don't have to remember le duck or whatever, however you pronounce that, because I remembered ruck, right? So obviously the left side is down and then counterclockwise. And that way these two opposing moments and forces offset each other, right? Because this is V going down. And then we just sum them. Whatever else we've got on the right-hand side, we sum that all together, just like I did in the last lecture. And I wanted to show you this, and I wanted to do that in the last lecture because now we're going to extend beyond that. We're going to extend beyond that, and we're going to realize that the loading diagram is the derivative of the shear force diagram, right? The loading diagram is the derivative of the shear force diagram. Or we could say that the shear force diagram is the integration of the loading diagram. So let's see what we've got here, right? So if it's the integration of this, first of all, let's just use this and figure out what the, the shear forces are. Well, I think everybody can see that right here we've got R sub A. This is how I do it. I'm going to show you how I do it. So we've got R sub A. Let's use the red pen. So I'm going to say, okay, well, we go up R sub A. Isn't that up, right? So we go up R sub A. This distance right here, right, is R sub A. Then, is there any force in between here? Is there any force that's going to change where we break that beam, just like I said in the last lecture? No, there's not. So that is constant. Now, what's the derivative of a constant? Right, let's do that. What is the derivative of a constant? So d dx of 5. That's 0, isn't it? Isn't the slope, aren't we really figuring out what the slope of this is? Isn't that what the derivative is? The slope of the line? What is the slope of that line? It's 0. Now let's get over to P. Remember when we got to P and we were looking at this other side? We were actually, saying, okay, well, what's going on if I was to break the beam here? And of course, now P isn't there anymore, the 100 newtons. So we've just got R sub B, which we know is 50 newtons just by symmetry, right? So what we do, look at where P is. P then is 100 newtons, isn't it? And you know what? This distance right here is 100 newtons. So I go up with R sub A. I go across because there's nothing there. I hit P. P forces me to go down, right? Because P equals, I need a better, thinner red pen probably, because P equals 100 newtons, right? 100 newtons. So it goes down. Then what happens? Well, I don't see anything else. There's no other forces here, is there? So I just continue across. Well, that's not exactly the same, but you know what I mean. 100 newtons, so this would be minus 50 newtons. This would be plus 50 newtons. Now, didn't I say that the shear force diagram that we have here is the integral of the loading diagram, right? Loading diagram, integrate shear force diagram. If we do that one more time, we get the bending moment diagram. And again, bending plus, minus. You're probably thinking, well, it's all going to be in the positive side then, right? Well, you know, we know that this is 0, so we know that the slope of the line in the shear force diagram has got to be 0, right? So that's 0, and if it's a constant, the derivative of a constant is 0. Well, let's integrate a constant. So if I take the integral of a constant, doesn't that give me a constant 5x, just using 5 as my constant? 5x plus c1? That's right. And so if we look here, we know that the slope of the line is going to be 50 newtons per meter, right? 50 newtons per meter. We also know at a simply supported beam, if I were to take it all the way to the end, the moments are 0. So the moments have to be 0 here. They have to be 0 here. We know that we're going to have a slope that is 50 newtons per meter, and it's positive, right? Well, doesn't that look like a line with a 50 Newton per meter slope going up there? We know that the slope has to be negative 50 newtons per meter coming down. So, well, it's 4 meters both ways. I didn't draw that. Oh, yeah, that's not bad. So it has to come down this way. Does that make it 0? We started at 0. We ended at 0. This is minus 50 newtons per meter. This is plus 50 newtons per meter, right? So that is our shear force diagram. Let's just color in our, or did I say shear force? I meant bending moment diagram. Let's just color in. I was thinking ahead that I had to color in my shear force diagram. So we colored in our shear force diagram. We've colored in our bending moment diagram. You know, what we don't know is what is the maximum bending moment, right? So V max equals what? And I think everybody can see in this example, the V max is going to be 50 newtons. M max, right? Sum them equal to 0. So we get that. And then let me just write down the things here. 4 would be shear force diagram. And then 5, and we've learned how to do the shear force, the simple shear force diagram. And then 5 would be integrate the shear force diagram to get the bending moment diagram, right? And that's what we've done. Now, when we've got 50 newtons per meter and we're going up 4 meters, what's that maximum bending moment going to be? So M max is going to be 4 times 50 newtons, 4 meters times 50 newtons, right? So 200, oh, you know what this should be? This should be 50 Newton meters per meter. right? Because that would come out to 50 newtons, which of course is what this is. The slope of the line is 50 newtons. So 50 Newton meters per meter, 50 Newton meters per meter. And that of course would give us 50 newtons, and that's what the slope of the line is. So if I were to do that, I would have 4 meters times 50 Newton meters per meter, and I think everyone can see that's just 50 newtons, right? So 4 times 50 Newton meters per meter is going to give me 200 Newton meters, right? So this point right here is 200 Newton meters. Does everyone see how I've done my shear force and my bending moment diagram for this very simple of all problems where I just have a simply supported beam with a loading in the middle, right? That you couldn't get any more simple than that. Now we've got 3 different types of beams that we're going to be looking at. We're going to be, I mean, over the course of the semester. I don't know if we're going to be looking at these all today, but I want to sort of introduce the 3 different types of loading that we can have on a beam. And of course, the first one is simple loading. And simple loading is a simple beam, a simple loading beam. You know, we've got supports at both ends. And then we're going to have forces. We might have distributed loads, you know, something like that, uniformly distributed loads, maybe other loads, but that's just a simple loading. And the reason we call it a simple loading is because it is supported at both ends. Now, another type of beam loading that we're going to be seeing is what we call complex beam loading, where I'm loaded at I'm supported at one end, but then I'm supported again someplace along the length of the beam, right? So this is called a complex loading, right? So simple loading, both ends. Complex loading, one end is loaded, but then the other one is off the end. And then we also have a cantilever beam or load. Sometimes you'll hear this terms of complex beam, simple beam. It's the same thing. So I thought I'd put the cantilever down here. Now the cantilever analysis for a beam is something that only has one end fixed. The other end is free, right? And so in a complex loading beam, we're going to have the same criterion as we do here. But with a cantilever beam, if I was to draw the bending moment diagram, the bending moment diagram at this end is still going to be 0, right? So let's just call this the bending moment diagram. At that end, it's going to be 0. But how is this going to bend? I'm going to exaggerate this a little bit, but it's going to, you know, bend down like that, isn't it? Right? Now, is that positive or is that negative bending? Because I've got the positive one that's bending like this, right? But this isn't. This is bending like that. So when I look at this, if I were to draw my shear force and bending moment diagram, this is all going to be negative, isn't it? Depending upon my load. Let's say that I've got a load P there, and I've got some type of non-uniform or you know, uniform load there, and I've got some other type of non-uniform loading here, right? Something like that, but it's going to bend down. So what we've got is we get a, let's see, that would be up like this, and then it would be straight, and then it would be up like that. So you can see that for a cantilever beam, almost the entire bending moment is, well, the entire bending moment is negative, but you can see that it's very negative when you look at the base of this cantilever beam being embedded inside a wall, right? Some type of brick or concrete wall or something like that. So we've got it embedded, and then we're going to have these, the maximum moment is always going to be here. So M max, usually, I could actually load this so that it's not, and in fact, that's what we're trying to do, right, is going to be here. So usually I have M max here, but I can modify this so that I could put a torque there, right? Some type of positive torque, and then that would cause this to shift. And we'll be doing those more complicated loading cross sections as we get into strength of materials, solid mechanics. But really in statics, that's the first place that we get an introduction to shear force and bending moment diagrams. And we really just want to, concentrate first of all on you getting a general understanding on how to integrate from the loading diagram to the shear force diagram to the bending moment diagram. And this extends further too, because if you think about it, doesn't this work out the same for velocity and acceleration too, right? Because if I have an acceleration, I could then draw a constant acceleration. Now let's just look at that. Let's just say acceleration is here, right? And I've got some type of thing. So my acceleration, let's just say there's my 0 line, and there's positive acceleration, there's negative acceleration, right? So let's say that I dropped something out the Empire State Building, right? I've evacuated all of the Earth, so there's no air. Or let's say I just drop it on the moon. Right? So I'm dropping something on the moon. It's got a constant acceleration, doesn't it? Right? So it's got a constant acceleration. What would its velocity look like? Well, if it has a constant acceleration and that constant acceleration is positive, then isn't this going to be positive? A positive slope like that? I drop it out the Empire State Building window, right? I drop a rock. I drop a rock out the Empire State Building window. The police show up and arrest me. But how does it go? Well, we've got a constant acceleration. And in this case, we could say that we know what this acceleration is. It's 9.81 meters per second squared, right? And if we know it's an then we can also come up with a velocity profile. And of course, the velocity profile is just, this is meters per second. Let's say that this is a time axis, right? And then how many seconds have I got? 1, 2, 3, 4, 5, 6, 7 seconds. So if it's 9.81 for 7 seconds, at the first one, it's going to be 9.81 meters per second, isn't it? And then if I was to multiply that 9.81 meters per second times 5 seconds, that would be, let's see, 1, 2, 3, 4, 5. That would be 49.05 meters per second. Does everybody see that right at that point there? No, it kept going. Now, I'm not so worried about what all of those are. I just gave you some numbers so that you could see how it all works together. But now let's go to distance. Right? So my velocity is increasing. My acceleration is the same. So I've integrated from acceleration to velocity. And now I want to integrate from velocity to distance. I mean, isn't that the equations that we have? We have A equals the change in velocity over the change in time. We've got v equals the change in distance over the change in time. And so really, if we wanted to work this out, can't we say, well, that's ds dt, and that's d. So isn't this a really d ds dt over dt? Let's do that again. A, right, is going to be d squared. Do you see the d's are squared and not the ds is squared? So d squared s divided by dt times dt, so that's dt, the quantity, squared, right? And then s, if we wanted to integrate again, v equals ds dt, so we could say that s equals the integral of v dt, right? And that's what we've got here. So if I was to integrate that once more, because this is just going to be c, this would be cx, right? And this is going to be, well, cx plus, or let's say c1, c1x plus c2. And this, of course, would be c1x squared plus c2x, right? Plus c or whatever. Yeah, plus c3. Now we can use border. Let's say that we've used boundary conditions and we found that C2x, C2 is 0 and C is 0. So what it's going to look like is something like this. It's just a parabola, right? A parabolic spandrel. And so that's S. And so we're really doing the same thing with this. A, integrate to V, integrate to S, as we're doing with this loading diagram, integrating to shear force diagram, integrating to boundary or to a bending moment diagram, right? And then we'll use boundary, initial conditions and boundary conditions to figure out what all of these are. And that's what we're doing. That's what I wanted to point out, that that understanding this is a crucial point in your development as an engineer. Being able to not only take equations and integrate them, but to take distributions and, and then integrate them. And then integrate them again. Just as we've done with acceleration to velocity to distance, right? Okay, well, that's great. We don't have a lot of time left, but what I want to do is just go into, some of the things that we're doing with this. Now, well, I actually saw that symbolically, so I'm not going to do that one. I actually want to give you guys some numbers. So let me grab a simply supported beam. I know I've got one right here. Yeah, here we go. So the next thing that we're going to look at, I'm just going to set this up. It's a little more complicated, but it still is going to, and it's also going to be a complex. Unlike the simply supported beam that we've just worked with, the second one that we're going to look at is going to be a complex loaded beam. All right. I just really want to set up the just take the next couple minutes to that we have, because I see that we still have a few minutes before this is over. So what I want to do is I want to set this up as a complexly complex supported beam. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I went one too far this time. But Yeah, actually, I could have left it. I could have left it there. Where is that? Because I'm going to break these up anyway. So yeah, let's just leave it at the 10. I'll get rid of that. I'm not really pleased with my new correct type thing, but I'll live with it. So the first thing that we're going to do is we're going to say that the supports now are not at both ends. I'm going to say that this is R sub B and this is R sub E. Just to change it a little bit, right? So we have two supports now. If I was to, on the thing, in fact, we could just draw those as supports, right? I'd just like to do that. And then I'm going to have a variety of different point forces. So we're not making distributed forces or anything yet. It's just going to be point force. So this is going to be 8 kilonewtons. Then, and this, let me just drop down some, this is going to be 5 meters. I might not have the thing to actually write in there, but that's going to be 5 meters. And then I'm going to have 6 meters. Yeah, I know, not drawn to scale. That's my disclaimer. So 5 meters up to R sub B, 6 meters to the next force that's going to be applied there. And that's going to be 10 kilonewtons. And then right pretty much next to that, I'm just going to drop this down, only 4 meters away, right, is going to be another force that's applied, and this is going to be 12 kilonewtons. And then from there all the way to the end, we're going to have 10 meters. I'm just going to put meters where I can, right? And we've got all of those 10 kilonewtons. And then at the end, we're just going to have the support here. Now, we're going to have some pretty heavy work to do with this in the next lecture, aren't we? I'm going to drop this down, drop that down. And then what we're going to do is we're going to put in a shear force diagram. Then we're going to also put in our bending moment diagram. And when we finish working through that problem, I think that everybody will know how to work with both a simply supported beam or a complex supported beam. Now, a complex supported beam, just like a simple supported beam, has moments that are 0 on both ends. Oh, we're done. So I've set up the next thing, and that's what we're going to do, is we're going to solve that. And in solving that and working through the problems, you know, with numbers and everything else, I think you're going to see how, you know, we set up the problem, and really it's just an integration. And like I say, very important thing for an engineer to learn, because there's a lot of relationships that work like this: acceleration, velocity, distance, loading, shear force, bending moment diagram. So we're, you know, learn how to integrate not just equations. In fact, who was it? It was Dirac, Paul Dirac, right? I'm just going to write this here, Paul Dirac. We only understand an equation when we can visualize it. I didn't really understand what Paul was saying, right, until I got to graduate school. And then all of a sudden, visualizing and understanding really what the equation is saying and seeing it. You know, it's like an epiphany when you get to graduate school and you finally start understanding the mathematics that you've, you know, supposedly been learning the entire time. All right. So on to the next lecture. It's going to be an interesting one. Shear force and bending moment diagrams are very interesting, and that really cements your deep understanding of mechanical engineering so that you can talk on a level with a mechanical engineer. If you can understand shear force and talk to a mechanical engineer about shear force and bending moment diagrams, he'll think that you're some type of super genius. All right. See you at the next lecture.